Why are threads so critical in computing, you might wonder? Well, to understand their importance, one must first grasp the basic concepts of threads, processes, and context switching in computing. Imagine a processor as a physical entity that provides a set of instructions, capable of executing a series of those instructions automatically. A thread, on the other hand, is like a virtual processor created in software. It's a minimal software processor in whose context a series of instructions can be executed. Saving a thread context implies pausing the current execution and storing all the data required to resume the execution later. Now let's introduce the concept of a process. It's a software processor in whose context one or more threads may be executed. So, when we say executing a thread, we're referring to executing a series of instructions in the context of that thread. But why use threads at all? There are several compelling reasons. Firstly, it helps avoid needless blocking. A single-threaded process will block when doing I/O, whereas in a multi-threaded process, the operating system can switch the CPU to another thread in that process. Secondly, threads can exploit parallelism. The threads in a multi-threaded process can be scheduled to run in parallel on a multiprocessor or multi-core processor. Lastly, threads can help avoid process switching, structuring large applications not as a collection of processes but through multiple threads. Moving on to threads and their relationship with operating systems, we encounter a significant question. Should an operating system kernel provide threads, or should they be implemented as user-level packages? The kernel solution proposes that the kernel contains the implementation of a thread package, meaning all operations return as system calls. This approach allows handling external events simply and efficiently. The downside is the potential loss of efficiency because each thread operation requires a trap to the kernel. The ideal approach attempts to combine user-level and kernel-level threads into a single concept. However, the performance gain has not generally outweighed the increased complexity. Finally, let's touch on context switching. The processor context is the minimal collection of values stored in the registers of a processor used for the execution of a series of instructions. The thread context is the minimal collection of values stored in registers and memory used for the execution of a series of instructions. The process context is the minimal collection of values stored in registers and memory used for the execution of a thread. So, to summarize, threads are virtual processors in software that enable efficient and parallel execution of instructions. Processes provide the context for these threads to execute, and context switching allows the operating system to manage execution effectively. These elements are fundamental to understanding the inner workings of computing and are key to unlocking its full potential.